button.
Okay, and Leonard, could you go ahead and drop your screen share for a moment?
Absolutely.
Well, I'll spotlight myself. So. Okay, can folks see me? Okay, I actually can't tell other than I've got a highlight. So welcome to the August Northwest C++ meeting. Tonight we have Leonard. We're going to talk about Python and C++ bindings. We'll get to that in just a moment. First, a couple of announcements. I don't see Brett. Chris, do you want to do any announcements for CPPCon?
Had to find my multiple mute buttons. We are still looking for volunteers, both on site and some online. People that are previous volunteers or have experience doing some of our media hosting would be very useful. Selection process is in process right now for picking which submissions are going to be presented, both online and on site. We had about 200 submissions, and there are a lot of really good high quality ones, which means I'm going to get bumped off the bottom of the list, I'm sure. But yeah, if you're looking to volunteer and you're planning on being in Aurora, for on site, give Brett a call. Also give Brett a call or a message for volunteering online. Thank you.
Hey Chris, as for volunteering on site, is the hotel open? The Gaylord Rockies?
Yeah, the hotel is open. Yeah.
Okay.
Yeah.
That's good to know.
Okay. Oops. Thanks, Chris. So one other announcement. Next month is lightning rounds or lightning talks for this group. So about 4 to 8 of you have mentioned you've got talks you're putting together. I've got one as well. So next month is going to be a little bit of a different style meeting. What we'll do is it'll basically be whoever wants to do a presentation. It'll be a 5 to 10 minute presentation. So 5-ish slides type of thing. We'll just kind of organize it right at the beginning of the meeting when we start. So anyone who has a presentation that's a short presentation, it's not enough for a full, it's not enough necessarily for a full talk, or maybe if you want to try something and see if there's enough interest for a full talk, this is the opportunity. It's also, please feel free to use it as a practice session for CPPCon. CPPCon has lightning talks, probably 3 nights out of the week and some mornings. So if you want to do a talk there and you want to, use this as a trial or a practice session, please feel free. And yeah, so that'll be next month. I'm not going to do a full formal sign up or anything. Just show up to the meeting, bring your talk. The first couple minutes of the meeting, I'll just collect a list, and we'll go from there. So this is the first time we've done it for Northwest C++ users group. Quick show of hands. How many people are thinking about? I know I only see 1 or 2 people from the talk mentioned this in the past. Yeah, Peter's got one. Anybody else have a talk you want to possibly do next month? Okay, I think we've actually got between 4 and 6 talks. Because every month I've asked this for like about the past 3 or 4 months in a row, and I've gotten different numbers of people, but it's also different people. So we're probably in good shape. In any case, with that, I'm going to go ahead and turn it over to Leonard, and he's going to present on C++ bindings for Python.
Right.
And let me. Okay.
All right. So can you guys see the slide, the first slide again?
Yep, looks good.
All right. All right. So, you know, the big question is, you know, why would you care about, you know, the interop between C++ and Python? They're vastly different languages. So, you know, why go through the trouble to try to glue them together, right? And, you know, since you are here, I'm sure you have something in mind. I'm going to list a few ideas. And if anybody has any other use cases in mind, I would love to hear about it. So the common things that come up when you want to bind C++ and Python together are the use of existing libraries. If you have some established library and you want to use it from Python, or vice versa, you may have a Python library and you want to use it from C++, you can do that. Another common reason is to speed up certain operations. You can implement things in C++. You can leverage you know, tricks which are not necessarily available in Python. You can leverage, you know, GPUs. That's a fairly common use case. You can, you know, you may need low-level access that's not, you know, expressible in Python. That's another thing that you can do through bindings. A bit, you know, the reverse scenario is when you want to add scripting to a C++ application. You may have a functionality that you want to extend through a more dynamic type of coding than, you know, recompiling, you know, implementing everything in C++ and recompiling it. So you can embed a Python interpreter and you can use that to script your application. You can have, you know, for example, a video game. You can have the game logic or part of the logic implemented in Python. So if you want to add new logic, you can just add a Python piece of code instead of implementing everything in C++. And a few other things I listed here. So before I go any further, anyone has any other interesting use cases in mind that they want to share? So I'm going to move next, and if you have anything, you know, please do share. Now, kind of, you know, hinted in the previous slide, or the thing that I mentioned is that there are two different ways of looking at gluing Python and C++ together. One of them is when you have a C++ module that you want to expose in Python. So you want to extend the Python language through C++. That's the picture on the right side. You have, you know, the Python interpreter, and then you have like a small extension written in C++ that you can use from Python. The other approach is to have a larger application where you embed the Python itself, and you extend the application through Python. The interesting thing here is that both scenarios are enabled through almost the same APIs. So even though they look vastly different, both of these scenarios, they're actually very similar in terms of the implementation, and in many ways they are complementary. If you want to, for example, host a Python interpreter and script your application, you are very likely going to expose some of the functionality or objects or types or functions from your application through the Python thing. So it usually goes both ways. So the next important thing I want to cover here is that there is not a single Python. Usually when people refer to Python, they are talking about CPython, which is the original Python implementation. And this is the thing that I'm going to talk about today. But I just want to mention that there are multiple Python implementations that are very different in how they do things underneath. They all aim to implement more or less the same language, but how they do it is very different. And why is this important when we are talking about bindings? Bindings are a low-level contract between the Python implementation and the external module or the external components that's outside the Python implementation. So it's very specific to a implementation. So if you are creating a C++ extension for Python for CPython, you're not gonna be able to use that extension unmodified across all the Python implementations. There are some efforts to kind of like ease the transition a bit, and PyBind, the library I'm talking about today, offers some level of source level portability across CPython and PyPy, which are some of the most popular implementations. But it's important to keep in mind that the binding, the extension mechanism is very specific to the Python implementation down to the version. So if you're targeting, if you're building and creating an extension that targets, Python 3.6 on Windows, you're going to build a binary version of that extension, and that's going to work only with the Python 3.6, the exact version that you are targeting. If you are building it, targeting Python 3.8 on Linux, it's kind of the same story. So it's something to keep in mind. It is a bit of a complication, but in practice it's not too bad since CPython is the dominant implementation out there. Okay. Now we are going to focus on CPython, and even looking at CPython itself, there are multiple options for creating bindings. And there are two major classes of approaches here. One of them is automatic bindings, where you have the library coming together with some form of tooling that will parse your C++ headers, will find out all the declarations, and will generate bindings automatically. These are the things I listed on the left side. The other approach is when you manually create the bindings, you define the binding for each function or type that you want to expose. All of this, in the CPython case, all of these approaches eventually will boil down to using the CPython extensibility interface. So CPython, the interpreter itself, defines a C API that is used to extend the Python interpreter or to embed the Python interpreter. So all of these things, they are more or less layers on top of that API. That is the one true entry point to the Python interpreter. And all of these things, they offer, they are wrappers, or they offer some additional functionality. The one that do automatic bindings, obviously, they provide the most additional functionality, since they will parse definitions and will automatically generate everything for you. At least that is the promise. In practice, that's a different story. So I will have to say I'm a bit skeptical of any automatic mechanism that is capable of giving you a immediate answer to the bindings. I will encourage everybody to try it. That's why I listed them. Some of them, like Swig, the first one, they go a bit further. They create bindings not just for Python, but for multiple scripting languages. So it's even more attractive. But today I'm going to focus on the manual binding approach, and I will try to explain why. What are the pros and cons of these approaches. So what I'm going to talk about today is going to be focused on PyBind 11, which is a C++ header-only library for creating bindings, for manually creating bindings. So it's kind of like on the right hand in my previous slide. What it is, it's a wrapper around the Python C API that I mentioned earlier. It provides a much more pleasant and easier way of creating bindings, but it all goes down to the same basic Python C API. So what some of the defining things about PyBinding is that it's a lightweight library. It yet is very powerful. It supports almost all of the C++ constructs, from functions, types, virtual methods, and many others. Everything is going to be listed. You can find everything on the PyBind 11 website. It also provides a source portability across CPython and PyPy to different Python implementations. So you do have the option of creating an extension once and use it across both of these major Python implementations. I have not used PyPy with PyBind 11, but that's what they claim. So I'm gonna jump in with an example that is lifted straight from the PyBind 11 documentation. So this is one of the most minimal examples. We have a C++ function, the int add, taking two parameters, returning the sum of these two things. So the way binding creation looks with PyPy is it's the bottom part here. So you have a PyBind module definition, which is more or less a wrapper around a initialization function. When you build the extension, you are creating a shared library, an SO file on Linux or a DLL on Windows, which gets loaded by the CPython interpreter. So when you do an import foo, there is some fancy logic going behind the scenes, but at some point the interpreter is going to look for shared libraries that match a certain naming pattern, and if it's found, it's going to be loaded, and this is one of the first things that gets called by the Python interpreter. You're going to get this function called. So this is where you define the actual bindings, and the bindings in PyBind 11, they're pretty straightforward. So the last line on the bottom here, it's all you have to do to define a binding for a function, for the add function. You always start with the name, and then you pass the address of the function pointer. And PyBind 11 will deduce the type of parameters and everything else, and will create the right binding for this thing. So you do this thing, you build it, and you can use it from Python. And again, this is lifted directly from the PyBind 11 documentation, which is excellent. So I'm not gonna waste time repeating what's in the documentation. So I just want to kind of give you a taste of how things look. And once you get started, it's really easy to find specific instructions on the PyBind 11 website. The only two things I want to mention beyond the documentation is some high-level points. So first thing is the mapping between C++ and Python. As I mentioned earlier, they are vastly different languages. So the styles and idioms are different. If you're just going to map one-to-one everything you have in C++ to Python, you're going to end up with something that looks very foreign and strange to a Python developer. And I mean, if your goal is just to have a way to call something from Python, maybe that's good enough. But if you are aiming for something that feels like a native library, there are a few things to keep in mind. Starting with basic things like naming conventions. Python has a pretty well documented style, so that's a good starting point. And then you go beyond things that that you can define in C++. So, for example, in Python, the name of the arguments are part of the a function definition. So, and they can be used when you call a function. So it's nice if you define a binding to also define names that you can use in Python. Another thing that is a bit different in Python is that Python has syntactic sugar for properties. So in C++, if you have properties, you either expose a data member directly or you have getter and setter functions. In Python, that would look kind of weird. It's much nicer to follow the Python ways and define things properly as properties instead of having getter, get foo, and set foo. Another thing is Python is a dynamic language, and this is something to keep in mind when you're creating a binding. One of the immediate things that you are going to see in an IDE is that even the best IDEs they have trouble once you're building expressions where the types are not immediately obvious. So if you're using something like a builder pattern from C++, where you chain calls to the same thing, that thing is not going to work very nicely in a Python IDE, because after the first method call, even though you are returning the same object to chain all the other calls, IDEs usually don't have the ability to infer that, and you're not going to get automatic completion in the IDE, which is a pretty loved feature. And there are a few other things that I am going to show you. I'm going to demonstrate in a second. Are there any questions? I don't want to move too far if there are any questions here. All right. So the second thing I want to mention that is it is documented, but it's very important. It's perhaps one of the most important thing that I would like to leave you from this short presentation is the concept of lifetimes and ownership, and the implications when it comes to bindings. And this is a general design point. So if you are designing your APIs carefully, you already have spent some time considering the lifetime of ownership of all the objects, and the bindings doesn't change that. At least it doesn't change it fundamentally. You just have another value that kind of like you pass it out. So this very simple example I have here, hypothetical example, you have a function that called create node, which returns a node pointer. And we can guess from the name that what it does, it allocates a new node, right? And we create the binding for it, which again is very simple, just a def call here, and we get a binding, right? The question is, is this going to work or not? Because what happens is that we created the node, and we pass the ownership to the callee. Once we once the C++ function exits the ownership of the node, the newly created node, is on the callee side. And the answer is that yes, things will work as expected, because by default PyBind 11 is going to use a return policy which will move the ownership to the return value. So the way the whole thing works here with the Python bindings is that you have the C++ types and objects and values on the C++ side as usual. Now on the Python side, you have Python objects, right? So Python objects are they have a reference count. That's how they are managed, plus a garbage collection for cycles. And when it comes to binding, PyBind 11 has this concept of a holder. So each Python object is essentially encapsulates a holder for the C++ type, and the default holder for a pointer when you're returning a pointer is it's conveniently enough it's a unique pointer. So this works beautifully in this case, but it's something to keep in mind because things will look a bit differently when you're having a slightly different scenario. So in this example here, we have a graph class which happens to own a bunch of nodes. So in this case, the graph instance owns all the nodes in the graph. And a common implementation of this idiom is to have a vector of unique pointers. Right? So on the C++ side, everything looks pretty nice. The lifetime of the nodes coincides with the lifetime of the graph object itself. When the graph object is destroyed, all the nodes are destroyed. So everything works great. Now, in this case, it's very likely that you are going to have methods that still return node pointers with the contract that you don't get the ownership of the node back. So you get a pointer, and the pointer points to something within the graph, but you don't have the ownership. So if you're trying to do the same thing as we did before, create the direct binding, things are not going to work great in this case because PyBind by default is going to take the ownership of the return node from the lookup node method. And guess what? Like if when the Python object gets destroyed, and as I mentioned earlier, they are ref counted. So if they just get assigned bound to something else, they're going to get destroyed, and then the holder inside it gets destroyed, and it's going to free the node, which is not what we want because the node itself is actually owned by the graph, the graph object. So the result is that some nodes may be destroyed twice. So to clarify the semantics here, a PyBind offers an explicit return policy. So it has a default return policy which does what I mentioned earlier. You get the unique pointer owning the return value, but you can change it. So another return policy is the return value policy reference. And in that case, what it says is that don't take the ownership of the return value. So in this case, the Python object is just going to wrap a pointer and is not going to do anything with it. It's just going to keep that pointer around, and when the Python object is destroyed, that pointer just vanishes, but nobody's going to try to deallocate that node. Unfortunately, this is still not what we want, right? Because what happens is if the graph object gets destroyed, you end up with a dangling pointer. So on the Python side, you have that pointer, but the graph object may be destroyed, and the node that is returned, you still have the pointer there, but it's going to point to something that has been freed. So dangling pointers are not great. The right policy here is the reference internal, which will not take the ownership, and it will also increment the reference count of the parent object. So what this means here is that when we call the lookup node method, we get back a node pointer. We are not going to own that. But I say, hey, while I have this node pointer, I want to make sure that the parent, the one that returned this node pointer, is also alive. So the way this works, and this is done through the Python reference counting, is when the return happens, there's going to be the Python value wrapping the node pointer is going to add a reference to the graph object. So as long as we have that variable, the graph is going to be alive. So even if, for example, the graph object on the Python side gets destroyed, the fact that we have a node variable on the Python side is going to keep it alive. And to make things even more complicated, this is a third case where it just shows that it pays to think about these things carefully up front, because debugging these things can be very, very challenging. So this is another version of the previous use case, except that right now the pointer is wrapped inside a value object, a handle. And the handle has value semantics. So we're gonna copy it around. So the reference policy is not exactly appropriate because it's not a reference, it's a value. So the handle, the type that is returned is a value, so the reference return policy doesn't apply. But we still want to have that reference incrementing on the parent. And this is the last thing that's highlighted here, the keep alive. It does exactly that. And 0 and 1, what it means, if you look at the method and you start counting with the return value being 0, then the first argument, in this case the this or self pointer, would be 1. So that means that the return value adds a reference count to the parent object. So this is, you know, the implementation itself is interesting, but the most important thing that I want to convey here is the importance of being mindful of the lifetimes of ownership. You want to design the bindings with this in mind. You want to have a clear definition of who owns what and reflect that in the binding, and everything is going to work great. So beyond this, again, the documentation is excellent. PyBind 11 has very detailed and verbose documentation, and I would like to spend the rest of the time with a live coding exercise. Okay, this would be a good time if anybody has any comments or questions. Okay, Lloyd, like, do you guys hear me, or have I been talking to myself for the past half an hour?
Nope, you're good. I can hear you.
Okay. All right, so then I'm going to attempt a live coding exercise, which I think is going to be a bit more valuable for getting a feeling for how these things work. Because I like to do things the hard way. I implemented the demo on Linux, and now I'm going to try to make it work for my Windows laptop. So there's a good chance that the whole thing is going to crash and burn. So please bear with me. All right, so can you guys see my Visual Studio Code window right now?
It looks pretty good. Is the font size okay for everyone? It's okay for me, but I've got a big monitor, so.
I would recommend to increase the size of the font, or make the window smaller such that it is automatically scaled.
I would.
Yeah, that's better.
Okay. That's gonna take some space from the windows here, but it should be.
That's looking a lot better right there.
Okay, so is this okay?
Robin,
Yeah, that looks better.
Okay. I hope that since this is screen sharing, I hope this is large enough. All right. So I can actually get rid of that stuff. So what I have here, and this is a synthetic demonstration. It's something I created, for the purpose of this demonstration. So it's not exactly a real use case. But what I have here is a toy data flow graph. I think this is going to illustrate some of the ownership concerns that I explained a bit earlier. So what we have here is this very simple toy data flow graph. I'm gonna scroll right here. So it's a data flow graph. What it does, it has nodes, and the nodes can be variables or binary operators. Variables have a name which has to be unique within the data flow graph, and the binary op can specify an opcode, which is in this case addition, subtraction, division, or multiplication, and it has a left hand side operand and a right hand side operand, everything is integers. So just for fun, everything it does here is just integer arithmetic. So the division is the usual like C++ division, which truncates towards 0. So this data flow graph has declare variable method, create binary op, lookup variable, can return the variables list, a dump to graph viz, which I'm gonna use a bit later, that can have a visual illustration of what's going on in there, and a clear method. So pretty straightforward. The nodes themselves, hopefully it's nothing is going to be surprising here. There is a base class node that has a virtual eval function that is going to return the value, the evaluated value, which for a variable is the value that is assigned to that variable, if any. So the variable derives from node, has the same eval stuff. The values, the variables can have a value assigned or not. If they don't have a value assigned, trying to evaluate will throw an exception, which is going to show how the exceptions propagate from C++ to Python. And it has a bunch of other, obvious methods here. It has an assigned method, which allows you to assign a value to a variable, and reset sends it back to an unassigned state. And the binary op is just opcode, left-hand side and right-hand side. And the eval is exactly what you'd expect. It's just a switch statement, 4 operations here: plus, minus, divide, and multiplication. So the goal of this exercise is to create a binding, expose this to Python. And as a additional constraint is we would like to create a binding without modifying this library. So for whatever reason, let's say we have this C++ interface or library, we want to expose it to Python, but we cannot modify it. All right, so there is a bit of scaffolding required to compile a binding. It is documented on the PyBind 11 website. It's nothing too terrible in principle, but there are some unpleasant details. So what I did here, I already took the liberty to create the scaffolding. I have a CMake project that builds the whole thing, and then I have a setup that API, a script which is common in the Python world to build and install libraries. So what I have right now here, if I just do Python so this script is gonna invoke the CMake build underneath. It's gonna build the extension and then install it. So everything is done for us. We don't have to worry about that. So I also have the scaffolding for the binding, which right now it's empty. There's just the module itself. But just to prove that it works, right now I'm going to start Python here. The name of the extension is NWCPP. Right, 1 second. So we can have this stuff, and we cannot do anything with it because it doesn't actually have anything. You can do help on almost anything in Python, which is going to tell us, well, so what it does, it tells us the name that we declare here. That's the doc string, and that's pretty much it. Like, it doesn't do anything else. All right. So let's start adding the binding. A quick comment. I forgot to mention this. This is a advice that you may or may not follow in your use case. Very useful to have Python virtual environments set up. If you're working with Python, you're probably familiar with the virtual environments. If you're not, they're just a way to sandbox instead of having a system-wide interpreter and starting hacking on, installing and uninstalling things in that system environment. Virtual environments can create small sandbox environments. So in this case, what I have this NWCPP here. I'm using Miniconda, which is one of the popular ways to create these sandboxes. This is the name of this environment. So if I create this extension, if I make a mistake or whatever, it's not going to affect my system Python. So it's a good idea if you're hacking on Python bindings to use venv or Miniconda, for example. So what I'm going to do here, I'm going to have this side by side with the. Okay, so we have the definition there. So let's start adding them one by one. We'll start with the dataflow. Sorry. There's the module and the name. And then we can start adding methods, right? So we're going to use different names, right? Like, speaking of Pythonic bindings, the Python names use a different convention. So this is how the binding for declare variable, for example, is going to look. And we're going to go do the same thing for create. Binding up. Variable. Okay, what else do we have? We have the variables one. Okay, and let's do the and finally the clear method. All right, so we're pretty much done with the data flow one, or at least a very crude approximation. I'm gonna copy and paste. I have already handy here. So, all right. So these other ones, I'm not gonna make you watch me type the whole thing. It's pretty much the same thing, right? So we have these three main types, right? We have the variable, the name, eval, assign, reset, eval. Okay. So I hope it makes sense so far, right? And you know, we're pretty much done. This is all I have for today. You know, we can stop here and so let's see if it works first. So I'm gonna all right. So it built, which is very promising. Let's give it a try. So all right. So let's create a DAG. Unfortunately, on Windows, the completion doesn't work in the REPL stuff, so I'll have to type it to myself. All right, so we're not quite done yet. So we have everything for the data flow, but we don't have a constructor defined. So, all right, let's go back here and add a constructor. The way the constructors are defined is tiny bit different because, you know, constructors don't have names we can use. So PyBind came up with this syntax here, which is pretty convenient because in for the template arguments we can pass the type of the parameters, so we can actually specify which constructor, or we can even have overloading. We can have multiple constructors, but for now we only have the default constructor. So let's go back. We'll do the same thing again. Python. All right, so all right, it works. So we created a data flow object, right? We can print it. You know, it's going to be a very generic representation like this, but we can start using it. I mean, we already have the binding for most of the things, so we can say DAG here, declare a variable. We can check that. Okay, so it says we have a variable there. It's printed kind of ugly, so it doesn't make a lot of sense, but it kind of works. And then we can say like this, tag create binary up. We can say A. All right, so it complained about something here. So the okay, so we hit a small snag here, right? Because the create binary up takes two nodes, right? But we didn't define the node type itself, right? We only defined the variable in the binary up. So things are still not quite working. So let's add the base class. I actually have it here. I'm going to copy and paste it because we don't have a lot of time. And we can actually say that these things derive from node, and we can use inheritance. Like we can actually bind the inheritance part. Like we don't need the eval here and the DAG method here. So that also simplifies things a bit. So
I think you've got a typo on line 20. You've got not node or none where you need node.
Okay, thank you. That's a good catch. That's supposed to spell node, indeed. All right. And same thing here. All right, let's give it another try, right? So we are making some progress here where okay, we can say okay, and then we can say result oh, still not working here. Okay, so
I think you forgot to set up in between.
say that again.
I think you forgot to run the setup.py in between the changes.
You know, it's embarrassing it may be, you know, that is totally possible. Totally possible. So okay, so we have no variables, variable A. Down the result stuff. Okay, wow, so now it worked. So we have a result. So if we print result is just a Python object, but we can do we can try to evaluate that. Now, this is not going to work because we didn't assign any value to variable A. So from C++, like we can actually see the piece of code here on the C++ land. If you try to evaluate a variable, it's not going to work. We are going to throw a std runtime error, and very nicely that exception gets mapped and propagated to Python. So we get like a nice runtime error here in Python. So I think this is pretty nice. You know, so error handling works kind of like what you expect. You don't have to change things too much. Let's try to assign a value here, and we got, you know, 2 times 2 is 4, so you know, not too bad so far. Now, I think we still have some problems here. So what we have here, we have let's go look at the bindings again. So we declared a variable, right? And the declared variable, what it does, it returns a variable pointer, but the variable itself is owned, all the nodes are owned by the data flow. So let's see what happens here. So our variable will assign it to none, and then the tag is assigned to none. Okay, so we are in Windows here. Like this is less spectacular than on Windows. The Python interpreter crashed right now. We didn't see the segmentation fault. What is the
Error level.
error level? Okay, that's what I get for switching. Okay, so error level, right? So that thing crashed abnormally here, because when we assign none to A, the Python variable A, the reference count got decremented. It freed the node, and then when we freed when we did the same thing to the DAG, it freed the same thing again, right? So that's not exactly that great. So Lloyd, how are we on time here? Because it's already 8 o'clock, and I can skip a few things if we want to stick to the.
Yeah, we could go a little longer if you want. How are people feeling for questions? Do you want time for additional questions or time for additional demo?
Well, I prefer both.
Feel free to go to like 8:30. That's fine. So maybe 15 minutes for each.
So let's do an exercise here, like, because it's already like set up nicely. So I have a tracing for the lifetimes, which all it does, it logs to the console when a variable, when an object gets created and destroyed. So so let's see what happens in this case, and let's attempt to fix this, and then we can move to something more interesting. So Python again. So we'll do tag. All right, so we see a bit of logging here. So the data flow object was created, and we'll do the variable dance. All right, so we got a variable, right? Now, what happens when we did the non thing here? Variable got destroyed, and then this one got destroyed, and it actually crashed before it got a chance to print the other thing. So what we want to do here is the thing I mentioned on the slides. Go back here. I have to use the reference internal return policy. Okay, and I'm gonna just recompile to see the difference. Okay. All right, so nothing crashed, which is kind of what we want. What do we want to do here? We want to go back and fix all the declarations, because this is not the only binding that has that problem. So lookup variable has the same thing. So let's review them quickly, right? So declare variable has the same, is the one we just fixed. Create binary up is exactly the same situation. We just want to use the same policy. Lookup variable, same thing. The variables one is a bit interesting, because what do we do here? We return a vector of variable pointers. So what we want is, thanks to PyBind 11, this is going to map really nicely to a list of variables on the Python side. But what we want the individual variables inside that list to add a reference to the data flow object. Thankfully, the way that mapping works, the return policy gets propagated to the values inside the vector or inside the list. So it's a bit of a tricky thing. If you think for a moment, you'll see that you can create a test case where you extract the variable from the list and then you destroy the list, but you still want to keep the data flow alive. So again, thankfully, the way PyBind works gets this stuff done for us. and I think that's the only places we have to fix here. So what we are going to do right now is, because this is a bit verbose, let's see if we can do something a bit nicer. So we just defined ref policies. I'll give it a shorter name essentially. Ref policy, and this is going to be the exactly same idea for create this one, and for the variables. All right, so I think we fixed that part. The next thing here is it would be nice to have a nice printout for the variables, because if we are in Python and we print a variable, we just get a generic thing, just a pointer, just an address, and it's not very useful. So I do have a few things here already set up, so I'm just going to copy and paste. So let's add that part. This is just some helper functions that, you know, take a variable and a binary up and they return a string representation, a really basic one. And in order to use that stuff, the only thing we have to do is we define a method with a special name. So Python, and this is documented on the Python website, has a bunch of these magic methods. That's how it does operator overloading and a few other things. So REPL provides a string representation of an object. So we are going to just say okay, so this is one thing, and the same thing for the binary up.
Is that repr?
Sorry, what is the question?
I thought that was REPR.
Oh yes. Okay, you know, it's late. Thank you for catching this. Repr, that is the right spelling. And okay, so so let's okay, and so if we print A, let's see what happens here. So we get a nice printout for A. So, you know, we can do like as fancy as we want. You know, there are some finer points here, like repr is supposed to be a round trip representation, so you're supposed to be able to parse it back. We're not gonna go into that level of detail here, but the idea is, you know, you want at very least the friendliness of printing a human readable value here. So at this point, let's revisit what we have so far, and we can see how we are on time. So we have the basic bindings working. We have the return policy, which give us the right semantics. We have the repr stuff, which is pretty nice. Now there are a few things we can add. Yeah, so let's do one more round of cleanup here. So first of all, I mentioned, you know, in Python we want to have a name for arguments. We have to declare that explicitly. So really easy with Python 11, just adding this stuff. I'm just gonna add it to this method here just to illustrate it. And also, instead of calling variables like a function, let's make it a property. Okay. So variables, and that's kind of the only thing we need here. So let's check you know, these small changes to see what we have. All right, so everything builds. That's pretty good. And typing this stuff here in the Python interpreter gets a bit old. So let me try one thing so we can make it a bit faster. So let's use a Jupyter notebook. I'm not sure if anybody's familiar with Jupyter notebooks. They're just a fancy interface around the Python kernel, which is just an interpreter. So in this case, if we use the same one, everything should work. So let's do, okay. All right, so we worked. Now we have something that's a bit nicer and more persistent. So DAG, get a computation that's much nicer. We have a okay, so we have that stuff, and now we can say DAG that variables instead of calling it as a function, and we just get a nice list here. Oh, we can also use the second thing that I added, the name for the variable. So we can say name, which is a bit silly in this case, but once you have more parameters, this becomes very handy, and it's pretty convenient to have. So we go back here, we can rerun this cell. That's another nice thing in the notebook, and we have a list of 2 variables. And this is actually, I'm gonna show like what I meant by the ownership with the variables being more difficult. We can say let's see this. Okay, and then we can say now here if vars adds a reference to DAG, that's not good enough because we also have X laying around. So we can say vars. So X should still keep the reference, the DAG alive. So that happens. You know, it's it may require, you know, like to sit down and think for a moment about how these things work. But the good thing is that it works right now. So let me save this stuff because this may be useful. Okay. Now, in the interest of time, right, there are a few more iterations that we can do here. So adding the properties is one thing. Another thing we can add, and I'm just going to copy and paste, but I'm going to try to explain it really quickly, is some convenience methods. So in dataflow, we have this create binary up where you pass, you know, the operator and then the arguments. Now it gets kind of old to like pass that thing all the time. So let's define something like this. We can define some methods: add, subtract, div, and multiply, which just add, you know, will do exactly what we want. Like add will create a binary output plus. So with Python 11, you can use lambdas like this, and essentially you can fabricate methods on the fly if you want that don't exist in the real type in the C++ side, which is pretty convenient in many cases. So we define this add, subtract, divide, and multiply. I think it's kind of self-explanatory, right? So that's pretty nice. We can take it a step further, and we can do a bit of operator overloading. So this actually is going to look even nicer. Let's see if this is going to work. So this time we are going to try to have the nodes themselves, when we declare the variables or the intermediates, the temporaries, we give them names. It'd be nice to actually be able to use them and use the operator overloading to build expressions with them. So what we have here, let's see, I'm going to try to copy and paste what I have and see if it's going to work. So this is going to define the methods on the node itself, because, you know, operator overloading is going to work on the node types. And they have these special names, which is again like how Python does operator overloading. So add, sub, true division, which is the slash, because Python also has the floor division, the double slash. So these look exactly like methods. The only difference is this pi is operator annotation here. This is another piece of metadata that will get us the right bindings. So let's see what we have right now. First of all, let's see if it builds. Okay, so it built, and I do have some very basic test cases that the final version should pass. So I'm gonna do the same thing before we set up PI test, and this is gonna run the test cases. Let's see if, all right, so we actually have a failure here. All right. So let's see which one failed. Dataflow variables test case. Okay. Variable lookup. Okay, so this is I think I know why. Like for the variable lookup, I'm also going to add the named arguments. Pi arg. Added this stuff. Let's see if that's the only glitch. Okay, we still have another failure, which is pretty nice for the, it shows that the test cases are useful. A variable, okay, so data name, oh, okay. That is another thing that we didn't do in the binding. So the name of the variable. So this one, we want to make it a property. There are actually quite a few more that can be made properties. Okay, let's okay. All right, so all the test cases passed right now. So that's pretty promising. The final thing that I'm going to show you here, and we can hack a bit more if anybody has any ideas, is a notebook, although this is the old interface. So let's, okay, so this is another notebook that I used to test a few things. Okay. All right, so we're able to run this stuff. So we have a bunch of variables here, just to show we have like the 4 variables. This one is gonna create a slightly more complicated expression in there to work. Now I'm gonna show you the graph viz, what it does. So that's a way to visualize what's inside the graph. It just uses a tool, graph viz, if you're familiar with it. I can actually show you what's inside the graph viz. It's just a very, very simple definition for this graph, but we can see that indeed we have the variables plus the, and does this stuff. We can assign values to them, and then if it evaluates, if you follow it, actually it's the right value. Another thing is just to show, like, how natural things can feel in Python right now, because we define the variables as a list. Okay, this is going to fail because has value has to be a property. So I still have to make that change. I'm going to make the change here. Let's see if this is going to work. So we can print the variables like this. So at this point we have, I think pretty decent mapping, from C++ to Python. Let me think. Yeah, I think we cover pretty much everything. And if we want to stay until 8:30, we have 10 minutes for questions.
So go for it. You guys want me to moderate? Just raise your hand, or otherwise, just pop out and ask a question. No questions? Oh, there's one. Go for it, Chris.
Not necessarily a question, but earlier you had asked if anybody has any possible uses for this. And actually, in our project, probably 3-4 years ago, we actually used a Python to C++ layer where we had a Python application with a Qt UI shell, but Python was way too slow for we were doing some really super intensive, memory intensive operations. So we would drill down, call it into a C++ Python extension, do a bunch of code there, and then return the answers back. And we would actually call Qt interfaces from both the C++ and the Python. And we had a canvas area where we would draw schematic drawings in there. We would do wire trace routing and that type of stuff. So it's pretty powerful. It was a different flavor of the mapping than what you're doing here, but it's the same idea. And because it was a Python shell, we were cross-platform. So we would both test on Windows desktop and run in the WSL. We just had to have a GUI host to run through. I think, I can't remember what it was we used. But it works pretty well. So.
Yeah. I mean, you can get pretty far with the bindings. Did you use the Qt bindings for Python? So did you implement the GUI part in Python?
Yes, we did. Okay. And we would draw the widgets up there. We would load the menus, and we had our own little toolbar type mechanisms we had. And this was under a Python 2, not a Python 3, but it's almost the same type of thing.
Yeah, it can get pretty far with kind of like combining the power of both languages. I mean, I found out that Python doesn't scale in terms of size as well as C++. So after you get to a certain size of the project, it gets kind of difficult. But for small things, it's very productive.
Yeah, and we needed the number crunching ability of C++. And once we go into the C++ side, then we could go multi-threaded also. Where
right.
Python is not very good at multitasking.
Yes, that's a very interesting thing, and that's another thing that we don't have time to dig into today. The threading model, Python and C++. But yeah, that's a very good observation.
Okay, thanks, Chris. Other questions? Okay, going once, going twice. Okay, well, thank you. Yeah, so Leonard, if you could actually get your slides to me, and if you've got any sample code, I'll get that posted along with the video.
Yes, so what I'm going to do, I'm going to send you the slides, and this small demo project that I have here, I'm going to put it on GitHub.
Okay.
And I'm gonna add the link to the slides so you can send them together.
Perfect.
Okay. Yeah, and if there's anything else, if anybody has any ideas, feel free to reach out and let me know.
Yeah, thank you. This is excellent talk. I've been waiting for you to do this one for quite a while, actually.
I know. Thank you for your patience.
Yep, no worries.
All right.
Oh, that's right. We can do clapping hands in this one. I forgot about that.
Awesome.
There we
Thank you.
go.
Well, I hope it was useful. Yeah, and if you have things on GitHub, I'm going to put the thing on GitHub, and if anybody has ideas or you find issues, just open issues on GitHub or send PRs, and I'd be more than happy to help if anybody has questions.
Awesome. Okay, thanks again. And just one last little shameless plug for next month. Remember to bring your lightning talks, and we'll see you in September.
Okay, I stop
actually,
recording.
Robin, you go ahead and stop the video now too.
Okay.